Hello and welcome to Elektor Engineering Insights, the show that puts your engineering challenges to the industry's experts. I'm your host, Stuart Cording, the electronics reporter. Electronics is finding its way into everything, but each of those things requires power. If it's portable or remote, it will probably need a battery. So to deliver the best possible battery life, embedded system developers need to use every energy-saving technique in the book. But what about wireless systems? Who's making sure their protocols are not overly power hungry? Then there's the discussion about replacing batteries as a power source. Batteries are impractical in some cases and in others just no longer necessary as alternatives emerge. So under what conditions can energy harvesting approaches be considered a realistic alternative energy source? To find out more, my panel of experts for this episode are Dhiraj Sogani of Silicon Labs and Rodrigo Mesquita of Nexperia Energy Harvesting Solutions. This episode is sponsored by Elektor. If you like electronics, you'll love the articles, projects and insights you can access as an Elektor member. Our global design community has hundreds of thousands of active members and more than 1,000 contributing experts. You can go traditional and get our magazine delivered to your door, or go digital only and read only online. Either way, you get access to years of information and projects, as well as our active community. Follow the link below to sign up today. Now, we are pre-recording this episode rather than being live, so unfortunately we won't be able to pose your questions to our guests as we usually do. However, feel free to post your questions in the comments and we'll do our best to get back to you as quickly as we can. You can also reach out to me on LinkedIn or via Twitter using the hashtag ElectorEI. So let's get started by exploring how Wi-Fi is adapting to the needs of low-power IoT applications. I spoke to Dhiraj Sogani from Silicon Labs to learn more. So welcome to the show, Dhiraj. It's great to have you on. I'd like to start by asking you if you could tell us what your role is at Silicon Labs and where it is in the world that you work.
Sure. Thanks, Stuart. It's nice to talk to you again. And certainly I'm looking forward to our discussion today. At Silicon Labs, I'm responsible for all wireless product marketing, which includes Wi-Fi, BLE, and all the other wireless technologies which are used for IoT devices.
Now, for years, I think when we think about IoT, Wi-Fi is sort of like the last low-power wireless technology we'd consider putting into a battery-powered IoT application. It's sort of always been considered to be a poor combination, and all the other wireless technologies are there for when you really need to go to the lowest power. But I understand the Wi-Fi specification is changing. What's going on in Wi-Fi?
Yeah, that's a very good question, Stuart, because certainly if you really look at the Wi-Fi, it started off with a technology meant for laptops, cell phones, right, which are not as power hungry kind of devices. And what has been happening traditionally is people are using the Wi-Fi, which we call as traditional Wi-Fi, for IoT Wi-Fi applications, which is not the correct usage. IoT Wi-Fi is completely different. You need to redesign it for IoT devices, which are power sensitive devices. They could be small form factor kind of devices. They need lower cost. They need to operate with microcontrollers, which are extremely small. So in fact, if you look at the parameters for IoT devices, they are completely different from traditional kind of devices. So what has happened is if you start using the traditional Wi-Fi, it's not going to work. So now there's a whole class of new Wi-Fi solutions which is coming up, which is really meant for IoT devices. And this is where, in fact, our first generation Wi-Fi, which is RS9116, which is Wi-Fi 4, is extremely beneficial as well, because we have redesigned it completely grounds up for low power IoT devices. Because when you're talking about power consumption, you really need to look at it from a system point of view. From a device point of view, you really need to wake up, you need to transmit, then you need to go back to sleep as soon as possible to reduce the energy consumption of the whole system. So this is something which is very important. So for our Wi-Fi 4 devices, which is RS9116, we have done that extremely well, and now we are able to bring the battery life down significantly, where we have provided, in fact, I would say even more than 2x improvement in some of the applications like smart locks. But in addition to that, what has also happened now is Wi-Fi 6 has come in. And Wi-Fi 6 has introduced additional parameters which enable low power IoT devices even further. So there are some technologies called TWT, which is target wake up time, and there's OFDMA, which enables a better use of spectrum. Combining these two technologies, you can further reduce the energy consumption of an IoT device. So combination, I would say, of system level approach
Yeah.
as well as technology itself can lead to significant reduction in power.
Now, obviously, when we look at all the different types of Wi-Fi technologies, is a little bit become a little bit confused, isn't it, over the years? Because we have the IEEE standards for Wi-Fi, but we also have some sort of like marketing terminology. So Wi-Fi 4 is 802.11n, which is a 2.4 and 5 gigahertz technology. I mean, for an IoT application, one of the concerns is obviously as the transceiver and transmission frequencies increase, the power required and also the power required increases, the range reduces. Do IoT devices have to support both 2.4 and 5 gigahertz?
Sure, this is another very interesting question because if you really look at it, 2.4 gigahertz is certainly much better as compared to 5 gigahertz, as you just indicated, right? 2.4 gigahertz can give you much longer range. It has much better performance around the corner, specifically when you're inside a house. Corners are there, right? So where the performance can go down if you're talking about 5 gigahertz. Then it is lower in power, it is lower in cost. But what started happening was specifically in home environment, a lot of new devices started coming up, right? So now if I look at a smart home, you may have 50 to 70 or even increasing to 100 plus devices in a home. And because of the number of coexisting devices and all of them operating in the same 2.4 gigahertz spectrum, the spectrum was becoming very crowded. And this is where Wi-Fi 4 started creating problems. And people thought, okay, maybe we really need to look at now 5 gigahertz because 2.4 gigahertz, you cannot have too many devices operating at the same time. And this is where, in fact, Wi-Fi 6 now steps up, right? So Wi-Fi 6 has introduced technology called OFDMA, which enables a lot more devices to coexist in a 2.4 gigahertz environment. Now, from really, if I look at it from an IoT device point of view, there is no need to use 5 gigahertz anymore now because the issue which was associated with 2.4 gigahertz has gone away with Wi-Fi 6. Having said that, there will always be some applications which will need 5 gigahertz. So because 5 gigahertz certainly provides higher throughputs. And there are some environments where 5 gigahertz is mandatory when you're talking about, let's say, maybe a medical environment, some industrial environment. You may certainly need 5 gigahertz, but there are a lot of other devices where 5 gigahertz is no longer really required.
Super. So as we said, so the marketing terminology Wi-Fi 6 is related to the standard 802.11ax, and this covers also both the 2.4 and 5 gigahertz frequency bands. Now, most of the people's expectation as consumers is that the next generation of Wi-Fi is always going to be more connectivity, better support for a large number of devices, and that gives us the ability to stream to our TVs, stream to lots of laptops and handsets and tablets, and handsets and things like that in the home. But there's also been quite a lot of work done to support the challenges of IoT devices, the fact that they really need to be off quite a lot in order to save power, or at least have some sort of sleep capability and not be active all the time, which is something that's part of the Wi-Fi specification normally for normal devices. So what are the new mechanisms that have been added into Wi-Fi 6 that are really good for low power IoT?
Sure, certainly. So if you look at power consumption again, right? So traditionally what people were doing was to reduce the power consumption. They were really putting the devices completely into shutdown mode, right? That's the best way to do it. But that's not effective because then you need to wake up, then you need to connect to the network, right? So that takes time, absolutely, right? So now, then there was this whole mechanism in which is present even in Wi-Fi 4, where you can really sleep for a small duration and you can control that based on either DTIM or listen interval. So that's something that you can do. So where the device still kind of, this is called as an IEEE power save mechanism, where the device still kind of stays connected, but it goes to sleep and wakes up at predefined times and sees if there's an activity for a particular node. If there is activity, it's going to go into full-blown wake-up mode and complete the activity and then go back into sleep. Okay, so this is a device, this is a mechanism which has been used by, in fact, Wi-Fi in Wi-Fi 4, and we can quite effectively use it for a lot of other devices. A lot of things like, for example, smart lock or sensor kind of devices as well. Beyond that, now there are some additional mechanisms, which is TWT mechanism, which is target wake up time, which is a very interesting mechanism where now the way sleep time of a device can increase significantly. It's really the device communicates with the access point on how long does it want to sleep. Because in a sensor, for example, some sensors, you may say, I want to sleep for, let's say, a few minutes, and then I want to wake up. So that is a pre-negotiated time with an access point. Based on that, the energy consumption of those devices can reduce significantly, because instead of now sleeping for a few microseconds or milliseconds, now you can sleep up for minutes and even more than that, right? So this is something which is significant in Wi-Fi 6, which is different from Wi-Fi 4. In addition to that, what is also happening is the efficient use of spectrum, which is OFDM-A, right? So, and the problem that happens with Wi-Fi 4, it uses OFDM, for example, right? In OFDM, the efficiency of the spectrum usage is not there. Because of that, there's a lot of collision which happens. So people have to retransmit. They have to really wait for their turn to transmit. With OFDM-A, you can transmit. In fact, and the collisions are quite rare as well. And because of that, the overall power consumption of the device also reduces. So these are, I would say, two additional mechanisms which have been added in on top of DTIM, UAPSD, WMM, some of those things which were already present in Wi-Fi 4 as well.
Right. Okay. So that's one of the other things I was going to mention, because I don't know if it's sort of as clear maybe what mechanisms already are there. So there's WMM, which is the Wi-Fi multimedia power source. That is I've understood at least is a sort of a buffering mechanism which allows packets to be stored until the node that it's targeting or prepared for is awake. Then you have delivery traffic indication messages, DTIM, which is sort of the router actually provides a beacon, doesn't it, regularly, and that helps everything to make sure that you're still connected to your router. And then we have the unscheduled auto power save delivery, the UAPSD, not difficult to say at all. And that's where the client sleeps, where there's no data to transmit, and just wakes to transmit its packet and then collect anything that may have been prepared for it in the meantime. So
exactly. WMM and UAPSD are kind of inherent mechanisms which the tools always use. But on top of that, DTIM is one mechanism which is a controllable mechanism which is used for sensors a lot. You can play around with DTIM. You can say, I want a DTIM interval of 1 or DTIM of 10. 1 means really you're doing 1 millisecond, then 10 means 10 milliseconds, right? So you're sleeping for that much amount of time, and then you wake up and see if there's a particular traffic for a particular node. So these are different mechanisms which are available in the prior standards as well. So Wi-Fi 6 has introduced TWT and OFDMA, which further improves the power situation of a particular device.
Now, one of the critical things when you're developing these low power applications is obviously trying to, microcontrollers are sort of one area where it is, you've got to make sort of choices as to what do I turn off, what do I turn on, how much do I use sort of static, active power, and the low power capabilities of a microcontroller. When I've got Wi-Fi and all those, these capabilities within the specification, how much choice is available to me as a developer to select and turn on and turn off and tune these low power capabilities over the Wi-Fi link?
Sure. So again, if I look at it, it's all about the use case of a particular Wi-Fi device, right? So use case could be as simple as a temperature sensor, or it could be, for example, you're talking about maybe a security camera, or you're talking about, let's say, a video doorbell. So every use case requirement tends to be different. If I'm doing, for example, let's say a wireless sensor, a temperature sensor, then in reality, a lot of it can be completely shut down. So you can keep on collecting the data on the temperature sensor. And depending upon how often do you want to refresh, you can go into an active mode and transmit the information and go back into sleep mode, right? So that's a completely different use case. Now, if you're talking about, let's say, a security camera, really maybe you want to wake up as soon as you detect a motion. So in that particular case, you can have a sensor which is detecting the motion. As soon as that motion is detected, you can go back into complete wake up mode and start transmitting as well. So similarly, now if you're talking about video doorbell, it's more latency driven. So as soon as you press a particular button, you want to make sure that that button gets registered, and the video transmission starts happening as well. So depending on a particular use case of an IoT device, the user has a mechanism of completely shutting down, in fact maybe a microcontroller, uh, with a very small microcontroller, because there is now a concept of big little. So you can have a little microcontroller which can stay awake, which is dealing with all of these sensors and all, and the big microcontroller can be turned on as and when required, right? So there are mechanisms which you can use depending upon the use case. So you can turn on and off the microcontroller, different parts of the microcontroller. Similarly, you can turn on and off the wireless side as well. So depending upon the use case, the user has all the flexibility, but it's, I would say, completely up to the user based on the use case to decide what can be turned on, what can be turned off. But the bells and whistles are available on the wireless side as well as the microcontroller side now.
Now, when these Wi-Fi 6 based nodes actually go and use these mechanisms, what happens to the established connection when they wake up? Is there anything that needs to be done, like acquiring a new IP address or authenticating a secure link, or can they make use of what was already established when they first initially connected?
Yeah, so that's one of the unique things, in fact, about the IEEE power save mechanism. Even in Wi-Fi 4, when you wake up, the connection is already there. So you are not really putting it into complete sleep mode. So you're maintaining some status which is related to the connection, right? And again, going back to my previous response on the use case, there is a possibility where you can say, I want to completely shut it down, because that always will reduce your power consumption to the bare minimum. But most of the cases you don't have to. You can always keep the connectivity on and just go live as and when required, depending upon the use case of a particular device. So
Is it
these mechanisms, whatever are there right now, for example, the TWT that I talked about, DTIM I talked about, all of these mechanisms are available. In fact, even in a completely connected state. So you don't lose the connection with the access point. You don't lose the IP address that has been assigned to you.
Of course, and if you were taking the choice to completely close the connection and re-authenticate and wake up, that would actually require more power, wouldn't it? Because you'd have to go through a quite long process of communication to establish the link and acquire the IP address. So it's sort of a balance then, isn't it? Of
Absolutely. But again, if let's say there's a device which is going to do that once in 24 hours versus a device which has to do it every few milliseconds, again, it's completely, I would say, use case dependent. If it's a sensor and sensor has to transmit once a day, it may be okay to completely shut it down, and when it wakes up, it connects. So it's really about looking at the complete data profile, understanding what is the energy consumption, where, and based on that, optimization has to be done in terms of which particular mechanism should be used to optimize the energy consumption of the complete system, right? So that's really where people have to focus on.
Yeah. Now, homes, offices, and sort of industrial sites are notoriously busy in these 2.4 and 5 gigahertz spectrums. And although Wi-Fi 6 is there and offers all these power saving capabilities for an IoT sensor, the challenge is, isn't it, that there's still lots of technology based on Wi-Fi 4 using maybe the transmission technology, and that will cause sort of interference on the channels and the communications in those bandwidths. So, what impact does that's something you can't plan for as an engineer. You can only plan for all the capabilities and the options that you have in the software and the specifications. So what impact does interference have on battery life and power consumption? And is there anything a designer can sort of do in order to improve things?
Absolutely. In fact, so interference has a significant impact on battery life as well, right? Because if, let's say, I want to transmit the data and suddenly I run into collision in the air, then in that case, I may have to retransmit the data. Uh, so that is something which is going to certainly increase the energy consumption of the device, right? So again, going back to use case, when you're trying to look at a particular use case, you have to take interference also into account when you're trying to decide for a particular system. That's an important part, because and it's going to keep increasing. So Wi-Fi 6 certainly has this capability which reduces interference because it has more efficient use of the spectrum. So you have to look at that as well. So if, let's say, you want to operate in 2.4 gigahertz, you have a large number of devices which are going to operate at the same time, and you have, let's say, not just Wi-Fi, you could have BLE and other 2.4 gigahertz devices operating there as well. So from a use case point of view, the decision has to be made whether it makes sense to maybe look at Wi-Fi 4, whether it makes sense to look at Wi-Fi 6. That's an important decision to be made as well. But moving forward, I would certainly say, if from a power point of view, Wi-Fi 6 certainly is going to be a lot more beneficial, and it has a lot more capabilities. And then people have to look at the interference and see how it can be minimized as well, right? So which channels to operate in, how do you switch channels? All of that is also important kind of decision making factor when you're trying to decide how to operate in Wi-Fi, either 2.4 or 5 gigahertz spectrums. But that, again, I would say that is all, I will put that as part of the use case, because if I'm trying to deploy in a home, that's a whole different use case versus if I'm trying to deploy in an industrial environment. If, let's say, it's very critical that I need to react in a microsecond, in that case, the design is going to be completely different as opposed to a reaction time of a millisecond or a second, right? So the use cases define which spectrum to use, how to use it, and when to use it.
Now, one of the challenges embedded developers and the rest of the team have when it comes to sort of these applications where low power consumption is the critical element is, sort of comparing all the options that are available on the market. There's obviously part of it has to be a microcontroller. The other part is the radio transceiver. And then we're talking about measuring often microamps, or jumps between microamps and milliamps, which is a difficult measurement to make with any sort of power tool. Normally, you need some sort of power analyzer dedicated to that sort of huge jump in current consumption. So how? And then, of course, the only other option that you have before you get started is just the data sheets, where you can you've got some numbers on a piece of paper, and sometimes they're a bit on the conservative side. So how do you help customers, design engineers evaluate sort of the options when it comes to microcontrollers and radio transceivers? And do you have any sort of power measurement tools that you have at Silicon Labs for customers to use?
Exactly. So, of course, as you indicated, right, the most crudest part is, of course, the data sheet. You can start looking at the data sheet, but that's very, very crude estimation, because when you're talking about your actual use case, the complete data profile, the use model dictates what the final energy consumption is going to be. The second level is really power estimation tools, which could be a simple Excel sheet where you say, okay, my device is going to stay on for X amount of time. And then after that, I'm going to transmit so many bytes or kilobytes or megabytes, and then I'm going to go back into sleep. And that is some mechanism that we provide as well, a simple kind of an Excel-based calculation. That again is the second level. The third level is really when you get into the actual design, you need to really measure at a very accurate level on how much energy consumption is there. So we have mechanisms in our kit. We have recently, in fact, released a completely new evaluation kit as well, which has a capability of automatic energy measurement capabilities there, which can enable the designers to do the measurement live when they are doing the actual code development of the microcontroller as well, right? So these are various tools available, and of course, it's very important, depending upon the use case, you have to make sure that you have the right resolution of the measurement tool. If your use case is such that you don't really care, let's say milliamp and all is okay with you, maybe that's good enough. But if there's a use case where you really need to optimize every little ounce of the battery, then you have to go down to that particular level and do the right measurements, right? So you can do the measurement while you are doing the, in fact, coding. Then you have to use the right power measurement tools, which could be power meters, which can give you a lot more information. So depending upon, again, the use case, if I'm using a battery sensor where a battery has to last for 3 years, I have to go down to the microamp level. If there's something which I can recharge on a daily basis, maybe a crude estimation is also good enough, right? And if it's something which is non-battery operated, wall powered, in that case, maybe even simple data sheet is okay. So depending upon where you are, you have to pick up the appropriate information and the appropriate tools to enable you to do the design.
So I was looking on the website, and I also saw some news recently from Silicon Labs regarding the SIW X917, which is an ultra-low power Wi-Fi 6 transceiver, and it's also got a Bluetooth integrated that in as well. So can you tell us a little bit more about that particular device and explain sort of how it supports those low power IoT applications?
Sure, absolutely. So our previous generation product, as I mentioned earlier, was RS9116, which was a Wi-Fi 4 product, which had Wi-Fi 4, Bluetooth Classic, and BLE. And that also was an ultra low power device. So what we did with the 917 was took it one step further. So in 917, we support Wi-Fi 6 and we support BLE. And this is the lowest power Wi-Fi 6 in the industry today. Okay, and we are carrying over whatever we did in 9116, which was more of a system level power optimization, which enables us to do optimization, in fact, at the microamp level, where we can wake up very fast, we can transmit the data, go back into sleep very fast. So that whole infrastructure was already present in 9116. We are carrying that over here. In addition to that, we have also added all the Wi-Fi 6 power save mechanisms, right? Of course, TWT is there, OFDMA is there. Because of that, we can reduce overall the power consumption of the system a lot more. So that's something which is very unique in this particular device. So it has an integrated Wi-Fi 6 capability. Of course, it supports Wi-Fi 4 and the earlier technologies as well. It also has a BLE, which is integrated inside it. It also has a complete Cortex M4, and which is meant for customer applications. In addition to the Cortex M4, we also have another microcontroller, which is a network processor, which is running all the stacks. So when you're talking about an IoT device, really you need all the wireless stacks, which is Wi-Fi stack, BLE stack, the networking stacks have to be there, the cloud connectivity has to be there. So all of that mechanism is already there. It's running on a different processor, which is a network processor. In addition to that, we have a Cortex M4, which is running in RTOS, and the customer can use the Cortex M4 for writing the complete application as well. So it is a completely integrated device meant for IoT designers, including a complete network processor, as well as a Cortex M4 and Wi-Fi and BLE connectivity, providing the lowest power consumption in the industry.
So one question I have quickly as well is Embedded World's coming up, isn't it? We're just a few weeks away. Will visitors to Embedded World be able to see this in action?
Oh yes, absolutely. So not just this, we have a few other major things also beyond this. Of course, 917 has Wi-Fi and BLE capability, and of course, Matter is coming up pretty strong, right? So people are talking about Matter. So we are going to demonstrate Matter running on 917. Okay, so Matter can run on Wi-Fi, Matter can run on Thread. So we are going to demonstrate the Wi-Fi portion using 917, and we have another device called BG24. In fact, an MG24, these are the two other devices. So we are planning to show Matter running on that as well. So that's an important part. Absolutely. It's a complete Matter solution, which includes Matter over Thread, Matter over Wi-Fi. We also have a Matter demo, which is for bridging solutions from Zigbee Z-Wave to Matter, because what is happening in a home environment, you have Zigbee devices, you have Z-Wave devices, which are there, traditional devices, and there are a lot more devices which are going to come, and they need to bridge onto the Matter network as well. So we have also created a bridging solution, which we are going to demonstrate as well. In addition to that, we are also announcing a couple of things there. So we are announcing a new product, which is, in fact, the BG27 product, which is a very low power Bluetooth device, which is going to be demonstrated there as well. So that's an important one. In addition to that, we are also going to show a demonstration of high accuracy distance measurement using Bluetooth technology. So this is a new technology which has been promoted by BTSig. We had demonstrated that at CES, and we are going to demonstrate that further at Embedded World as well. And then in addition to that, the final thing that we're going to do at Embedded World is also a major launch around an MCU. So we have Silicon Labs is traditionally pretty big on low power MCUs. So we have 32-bit MCUs, 8-bit MCUs as well, right? So we are planning to make an announcement around the MCUs as well, where we are improving the support for 8-bit MCUs, and we are also going to show a portfolio for a 32-bit MCU family as well.
Fantastic! It sounds very exciting. I'm looking forward to dropping by the stand to have a chat and see some of this technology in action in March. That's the 14th to the 16th of March in Nuremberg, Germany, for those who've not attended before or would like to join. So we're rapidly running to the end of our time, unfortunately, but what I wanted to finish with was one last question on that wireless SoC technology device. How does it look at Silicon Labs when we want to start getting into sort of hardware and software development? What sort of tools and development environment do you have in place, and how does it look with the software stacks?
Sure. So if you look at all the products from Silicon Labs, right, we have a few major pillars that we use across all our products. One of the pillars is, of course, power that we talked about, right? So all our devices that we are doing, they're all low power devices. We have all the techniques for power reduction for each one of the devices. Second pillar that we have is really all our security. And every device that we are adding to the security as well. The third pillar that we have recently started adding is ML. And that's one of the things which I forgot to mention in 917 earlier. We have a complete ML accelerator, which is built into 917 as well. So it enables people to do things like keyword spotting. So you can have some data processing there as well, to do some small machine learning devices on the edge. So that's the third pillar that we have. Now, the fourth pillar that we have is the complete software development environment, which is consistent across all the products that we have as well. So, and that is something that we have done across all the products. We have this thing, we have a solution called Simplicity Studio. Users get a very unified experience, whether they are designing with BLE or Zigbee or Z-Wave or Wi-Fi. So the complete solution is available as part of the Simplicity Studio IDE, which is offered by Silicon Labs. So this is something which is very unique, and this is one area where we put in a lot of effort, because the user experience is important. And if the user experience is not consistent and users are not able to develop the solution easily using our solutions, then certainly the adoption level is going to grow. So this is something that we have invested significantly in, and we'll continue making more and more investments to ensure proper UX and DX for the end designers.
Fantastic. Well, it's all sounds like a very rounded solution, and looking forward to seeing you all there at Embedded World to examine it in a bit more detail. I think one of the other interesting things that I found on the website, I was also looking around, is this white paper here as well, for those who'd like to dig into the details a bit further. It's called The Future of Wi-Fi in Low Power IoT Devices, and it gives a great overview of those mechanisms within this specification that supports these power saving capabilities within the Wi-Fi protocol. And I think it's very helpful to understand how you engage them and what they enable. And we're going to add the link to that white paper in the description below the YouTube video, and elsewhere where we'll be posting this as well. So Dhiraj, it's lovely to talk to you again. It's really nice to catch up. I'm really grateful that you've taken the time to talk to us today and give us all your insights as you do so beautifully. Have a great trip. I know you're away from home at the minute, and we look forward to catching up with you again soon.
Thanks a lot, Stuart. It was great talking to you, and certainly I always love our conversations. And looking forward to seeing you at Embedded World, where we can demonstrate all of these technologies. And one more thing I do want to leave out is really we have a whole series which is going on, a Tech Talk series, where we are talking about low power consumption as well. So we have a Wi-Fi series, we have a BLE series, we have a Matter series, and we have an LP WAN series. Please go and take a look at the Silicon Labs website, and you can register for the series as well, where you can get more information on how to optimize power for various kinds of devices.
Sounds like a great opportunity to learn more. Super. Thanks ever so much. Okay, now it's giveaway time. Firstly, congratulations to last episode's winner of the Microbit Tinker Kit. That was Ingo. Your kit is already on its way. To extend our thanks to you as loyal Engineering Insights viewers, this episode I have something for exploring IoT and RF communication using an Arduino. The SunFounder Kit comprises 2 Arduino shields and a pair of nRF24L01 2.4 GHz radio transceiver modules. Rounding out the package, there's also a Nokia-style LCD display, 4x4 matrix keypad, and a relay board for switching lots of loads. For your chance to win, simply visit the link shown below and enter the keyword low power, that's low power, with your entry. Good luck. So welcome to the show, Rodrigo. Before we get into the technology, could you just quickly introduce yourself and tell us what you do and where you're based?
Hi, Stuart. It's a real pleasure to be here. As you know, my name is Rodrigo Mesquita. I'm Business Marketing Manager of Energy Harvesting Products, and I'm based here in Delft, in the Netherlands. Thanks
Super.
for the invitation.
You're welcome. It's great to have you on. I looked at some of the technology at Embedded World last year and I was really fascinated with it, which is why I wanted to get you onto the show to talk about it in a bit more detail. So, what I'd say is, well, let's start with energy harvesting. Do you have some sort of definition in the context of electronic systems for people?
Sure. In simple words, I would say that energy harvest consists in local energy generation. Let's understand energy harvest like this. So imagine that you have a small application, right? And this application has the ability to convert an available energy in the environment, in the ambient, into electricity to power the electronic system, right? For such a system, you won't need wires to take energy into it, uh, and you don't need also the user intervention to replace batteries. And as you already can imagine, this brings several benefits, for the environment, economic benefits, and functional benefits as well for those who apply these techniques. So, if I can summarize, it's local energy generation, right?
Super. And so we've got local energy generation. What sort of the block diagram of an energy harvesting system look like?
Yeah, very interesting. So essentially, we have five blocks in an energy harvesting system. The first one is the energy source, right? The first one is the energy source. So this is determined by the environment where the application will be used. So is it light? Is it vibration? Is it temperature? Right? So for each of these energy source, we need to understand the availability of the source in terms of intensity and duration, right? So the first block is the energy source. The second one is the harvester, right? The harvester is the transducer, is that device that will convert uh, this available energy into electrical energy, right? Uh, the third block is the converting part, is the PMIC, the DC-DC converter, right? This system will take the energy from the harvest and inject into the application. But this injection is made with appropriate voltage and current levels, right? This is the core, the main part of the system, because we can always extract the maximum power from the harvester, right? And this is what we call maximum power point tracking. We are always searching for the maximum power of the harvester, right? After that, we have the storage, right? We have the energy storage element. Why is it needed if we are already harvesting? Because we know that we don't consume energy at the same time and at the same amount that we generate. So if we don't have an energy storage element, you will have a energy imbalance. So the storage element is a kind of it's a pool of energy, right? It will assure the energy balance in the system. And finally, we have the application itself. That is the gas, that is the customer for the energy harvesting system, right? It's the load fundamentally. So five blocks: energy source, the harvester, the PMIC, the storage element, and the application itself.
Thanks. That's really helpful because now we've got a really good, clear overview of all the elements that make up an energy harvesting system, and it's obviously quite complicated. There's lots of elements to putting it together. So
Yeah.
if an engineer is starting to consider energy harvesting as the source of energy for their design, what are the key things and parameters that they should really understand and know before they get started?
Mhm. Yeah, the key parameters are the extremes, right? The first and the last block. That is how much energy your application will consume and how much energy is available, right? So, in other words, the key thing here is to understand the energy balance of your system. This is fundamental, right? Because once you understand this, you can understand if you will consume more than you harvest, or if you will harvest more than you consume. In the first situation where you consume more, you will have just battery extension, right? So if your battery lasts 1 year, it can last 2 years, for instance, which is already a good benefit. But if you harvest more than you consume, right, you can make your application energy autonomous. So you don't need to replace battery, you don't need to recharge batteries. And this is the main objective of energy harvesting. So fundamentally, the energy balance is the key.
Now, on the energy source side, what are the different possibilities there? Because obviously we're typically talking about, I don't know, maybe so photovoltaic is something that comes into my mind immediately. So how many other choices are there, and what are the advantages and disadvantages of each one?
Mm-hmm. Yeah, the first one is, of course, light energy, right? Where we harvest using photovoltaic cells, right? Photovoltaic modules. And this is a very popular and cost-effective solution, right? This is why this is the preferred source of energy for this type of product. But we have, of course, other solutions that we can mention, for instance, to harvest thermal energy, right? Thermal energy is a good candidate when you want to make applications for industrial or residential environments, right? Because it requires a consistent temperature difference to generate energy by means of a device called thermoelectric generators that we can also call TGs. The main disadvantage of this application it is because it requires a heat sink, right, to keep a temperature delta. So if you need a heat sink, then your application tends to be a little bit bigger, right? So this is the disadvantage. We also can have kinetic energy, right? Kinetic energy is also a good option when your environment have vibrations or motion in general. And this kind of energy is usually harvested by means of a piezoelectric material, right? The main disadvantage of this harvester is the fact that it requires a constant, a specific frequency of this vibration, right? So it is very, very selective, let's put in this term. And the third one is the radio frequency energy, right? That is very appealing, very popular, because we have RF in Wi-Fi or whatever. The main issue here is because this energy is irradiated in very low power. So depending on the distance of your transmitter, you may simply don't receive any energy, right? So the energy available is low, right? So light, kinetic energy, temperature, and RF. These are the main types.
Well, once we've actually then collected that energy from whichever we've decided to be the optimum delivery mechanism, then there's the challenge, of course, of storing the energy that we've collected. So on that storage side, what are the options there?
Yeah. Interesting also, and it's very important first to understand that when it comes to energy storage element, these energy storage element must allow bidirectional energy flow. So you need to charge and discharge this element, right? So in this sense, we have two main types of device. There are the rechargeable batteries, right? Which have a huge energy density, right? What is energy density? Energy density is the amount of energy per space, let's put in this term. So battery can store a huge amount of energy in a low space, which is really good because we want autonomy, right, for our application. This device also has very low leakage, which is very good. And the disadvantage for these devices is because it has lower life cycles when compared to supercapacitors. The supercapacitors is the second type, right? They are fundamentally capacitors with high capacitance. Basically this. This device is good. It's very good because it has the ability to handle high peak currents. And in other words, this means that it has a high power density. So batteries, we have high energy density, and capacitors, we have high power density, right? Which is the amount of power per space, per area, right?
Yeah.
But the supercapacitors, we have a very fundamental problem, right? Because the supercapacitor, we have high leakage, right? So the capacitors leaks a lot. So this can be translated as an additional load to your system, right? The storage element itself can act as a load because it leaks. So yeah, this is the disadvantage. So batteries and supercapacitors.
Yeah.
Of course, we also have a third type that is a hybrid supercapacitors that are right in the middle between a battery and a supercapacitor, but it's closer to a supercapacitor, right?
Okay, super. So so we've got the energy coming in. We've got somewhere to store the energy once we've sort of processed it and sort of efficiently got as much energy out of our source as possible. What is it that then a dedicated energy harvesting PMIC does? What makes it different from a PMIC for other power applications?
Mm-hmm. Yeah, because a simple DC-DC converter, you will only boost the voltage, or you will only reduce the voltage to a given level, right? But when you have a dedicated PMIC, beyond the boosting of the harvester output voltage, you try to extract always the maximum power, right? This is the main reason to have a dedicated energy harvesting chip, right? Because they have what we call MPPT, maximum power point tracking. So we keep monitoring, right, the power that we are extracting from the harvest, and we try always to optimize this power, right, in order to have always the maximum power, right? In our chip, for instance, we have a very unique MPPT that is very fast, and it doesn't require open circuit measurement. So it's a good feature, right?
So in your portfolio of energy harvesting technology, can you sort of guide us through one of the products that you have that supports energy harvesting?
Yes. We are now releasing the NEH 2000 BY. That is our compact energy harvesting IC, optimized for PV cells energy harvesting. Among its features, we can highlight, of course, its high performance and low cost, right? It has a small bill of materials. You only require 3 external capacitors, and you don't need inductors. You don't need an expensive inductor for the energy harvesting. So all of these together will make your overall system cheaper, smaller, and more efficient. Just to you to have an idea, Stuart, the total assembly area for the NEH 2000 BY is just 12 millimeters square. So it's really small, right? It doesn't require pre-programming. And as I said, it has a very fast MPPT.
So what type of applications then are people looking to put these energy harvesting systems into?
What type of application? Yeah, in general, as we like to say, whenever you have an application that uses a coin cell battery or a AAA battery, this is already a good candidate for an energy harvesting solution, right? So for example, when it comes to TV remote controls or electronic shelf labels, sensors in general, like wireless sensor network, these are good application, good candidates for energy harvesting.
Super. That matches well with what we were talking about earlier, as I spoke about the addition of sort of new protocols to Wi-Fi 6, because they're making changes as well for IoT, and I'm not sure Wi-Fi 6 is a candidate for energy harvesting. Might be a little bit on the high power side for that, but obviously there's all those other IoT wireless systems as well. So with your PMICs as well, what's the best way to get started? Are there some development kits? Are there sort of design guides available on the website? Where should we be looking, and what are we looking for?
Yes, we are working now in releasing evaluation boards, right? And we also have, of course, data sheets, application notes, reference designs, and then it will be very simple and very straightforward to apply our solution to your design. So yes, we have several resources for that.
That's fantastic, super. So I think everyone will be going onto the Nexperia website to have a look and explore around to find out the information and get a bit more into the details beyond what you've had time to tell me today. We're running out of time, unfortunately. This has been really interesting, and unfortunately we'd have to come to an end at some point. So before you leave us, one thing I wanted to ask you is maybe if you could give us 3 tips. What are the 3 critical things that you really need to get right in an energy harvesting design?
Interesting. Yeah. 3 fundamental things here are, the first one I would say is the energy balance. For sure, the first thing to see is the energy balance, because you need to harvest more than you consume, right? And these, as you said, is a true optimization problem. You need to optimize the size of your harvester to your designing constraints, energy availability, and energy consumption. So the first thing is the energy balancing, of course. The second one is the price and complexity, right? Because imagine, since you are adding more items to your design, more components to your design, it must be cheap and simple. Otherwise, it won't make sense to add energy harvesting into a very cost-sensitive application, such as a small IoT device, right? And that's why our solution is very, very competitive when it comes to size, complexity, and price, right? And finally, efficiency, right? In this context, I would say that efficiency means to better make use of your available resource, right? So having a good efficiency, you can guarantee a cost-effective solution, since you don't need to over-dimension your system, and you will still mitigate costs, right? Once again, that's why our solution is the best solution for energy harvesting PMIC, because it's simple, low cost, and very efficient, Stuart.
Well, that's great, and I think if I'm correct, you're also exhibiting at Embedded World in March. Is that correct?
Sorry?
You'll be at Embedded World exhibition in March as well. Will people be able to see the energy harvesting in action?
Yeah, we'll be there with a demo with demo boards, and of course with all this kind of informations. You can find us there.
Super. Well, thank you ever so much for your time today, Rodrigo. Really appreciate it. And yeah, we look forward to seeing you at Embedded World and seeing all the hardware in action.
Okay, thank you so much. It was very interesting.
Well, that's about all we have time for in this episode. So what did we learn? Wi-Fi hasn't always been the first choice for low-power wireless, with many other protocols offering a power advantage. However, Wi-Fi is the only choice that's directly connected to the internet in people's homes and workplaces. Now, with Wi-Fi 6 and its additional sleep capabilities, coupled with its new signal modulation scheme, battery-powered devices and battery-powered IoT devices will be able to operate much longer. Then there's the question of alternative power sources. If you have light, vibration, heat, or even RF energy around your application, energy harvesting might be the answer. Thanks to PMICs with fast maximum power point tracking, the design of such systems is becoming easier, and it requires little space or component count on your circuit board. My thanks today go to my experts Dhiraj Sogani of Silicon Labs and Rodrigo Mesquita of Nexperia Energy Harvesting Solutions. You've delivered us with some outstanding engineering insights. So that wraps it up for today. If you'd like more of the same, we're broadcasting 2 episodes of Engineering Insights every month in 2023. And to keep you abreast of industry trends this year, take a look at our News Bites, a monthly 15-minute show. Please subscribe to Elektor TV Industry on YouTube and share our videos on whatever platforms you use. Or drop by the website at elektormagazine.com/EEI to see the topics for future shows. Finally, if you'd like to join me as a guest, write me an email, drop me a tweet, or reach out to me, Stuart Gording, on LinkedIn. Thanks for joining, stay in touch, and don't forget to keep asking your engineering questions.